be sharing something about diodes and its application, few of the application, like one of the application like rectifiers. So these are the topics where I'm going to cover today. PN junction diode. Simply we can say it as a diode or junction diode or PN diode, one and the same thing. Then one of the application is a diode is a Zener diode. How the Zener diode is made and what are the usage of the Zener diode, mainly as voltage regulator. And then again the usage of diode as in rectifiers. Yep, these are the few of the pictures of the diodes. You can see a lot of diodes over here. These are LED diodes. You can see the signal diodes. You can also see Stockley diodes, Zener diodes, pin diode, tunnel diode, laser, LEDs, point contact, and a lot of different diodes are there. So these are a few of the pictures of them. You can see how it looks physically. Now, just if you go back and understand exactly how it was invented and when. So it was invented in the year 1904 by the scientist called John Fleming. And initially it was constructed with two electrodes. I mean, like, you know, that particular diode was having only two terminals. And like one was anode and the other was cathode. And that was in the form of vacuum tube. Now these vacuum tubes are replaced by the transistors. So hardly we use any vacuum tubes in any of the practical example. Then in the 1906, a scientist called Lee Forrest added the third electrode. As I said earlier, it was having only two electrodes. Now he have added the one more terminal, and that was called as in control grid. And then that particular tube was called as in triode because it was having the three terminals. And basically the triode was used for amplification or like kind of a switch. Amplification, like amplifying the weak signal into a strong signal, we can say as an amplifier. Then the applications of triode created a new era in the broadcasting with the invention of crystal radio sensor by Pickard in 1912. Commonly used in DC power supply units as rectifiers, which we're going to see that, voltage regulators, which we also cover up in this particular video, clamper circuits. Maybe in the next class I'll take these two things like clipper and clampers. And as we have seen the pictures, it comes with different shapes and sizes. Now if you see the symbol in the construction, now here we can see the construction, like, you know, P-type and N-type. When suitably added by the process of crystallization, a junction is formed, and that junction is called as an P-N junction diode. So obviously this is the P-type material and this is the N-type material. So because P-type have the majority of charge carriers as in holes, it is a positive, and N-type have the majority charge carriers as in electrons, and it is as in cathode. And this is the symbolic representation of a diode, and here we are using an LED because two arrows are shown over here. It means it is a light emitting diode. And the other picture says the normal diode, and this is the one more kind of a diode. So this is just kind of a pictures. Now how it is formed? Made from a combination of two extrinsic semiconductors, P-type and N-type material. Now what are extrinsic? Previous class we have seen what are semiconductors, what are pure or intrinsic semiconductor, what are impure or extrinsic semiconductor. So when I say that, you know, when number of holes are equal to the number of electrons, then that can be called as an pure or intrinsic semiconductors. I mean, any semiconductor material in its pure form, is called intrinsic or pure semiconductors. What are extrinsic? If you understand, extrinsic is nothing but if at all we add any dopants to a pure semiconductor. It means if we add any impurities to a pure semiconductor, then that process is called doping. And obviously, when we add an impurities to a pure semiconductor, that pure will be again into its impurest form, and that particular new material is called an extrinsic semiconductors. So that extrinsic semiconductor, after adding impurities to a pure, so what kind of impurities we are adding? So we can add the trivalent impurities, or we can add a pentavalent impurities. As we add the trivalent impurities, because it's a trivalent impurity falls in the third group of periodic table, all the elements will be having 3 as a valence electrons. So the 3 of the valence electrons, if I take as a boron as an example for the trivalent, so 3 of the valence electrons of the boron will be having a covalent bonding with a pure semiconductor. Let us take an example of silicon, because silicon and germanium are the best example of semiconductor materials. So silicon is a 4th group element. So 4 of the covalent bonding of silicon will be 3 of the valence electrons of the silicon will be having a bonding with boron. But boron, because it have only 3 valence electrons, so one is lagging. One vacancy will be created, where which it is waiting for one more electron to have a pair to that. That vacancy is called hole, which is a positively charged. And that material which we form it is called as a p-type material. And we can also say that p-type material is called as an acceptor, because it is ready to accept one more electron for the pairing. Similarly, if I take an example for the pentavalent impurity, like any of phosphorus, bismuth, and antimony, arsenic. So if I take the phosphorus, because it's a pentavalent impurity, it will be having a 5 valence electrons. So 4 of the phosphorus valence electrons will be bonding with the 4 of the silicon valence electrons, and 1 electron will be excess. So that's the reason that is called as a donor atom, because it is ready to donate one more because it is having an excess. So this material where which a pentavalent impurity is added, a pentavalent elements are added to a pure semiconductor, that the new formed material is called as an n-type material. Now hope you are very clear with p-type and n-type material. Now how the junction is formed. So when we take a p-type material and an n-type material suitably added to each other, a junction is formed, and that is called a p-n junction. So we will be having 2 terminals, and that is called as an anode. One is called as an anode towards the p side, and cathode towards the n side. Normally this is produced from a silicon wafer, what we can see here. What is the construction? What is the construction of p-n type? What will happen when p-type material is added to an n-type material? Let us understand that. So here you can see the electronic device that results from the fusion of p-type material and n-type material. This is a p-type, okay, and this is an n-type. We have taken 2 different shades so that we can easily understand. So this is a p-n junction representation, and junction, I'm like in between of these 2 material, we can see the different layer, and that different layer, different color layer which we have shown over here. This is called a depletion layer or depletion region. How it forms, we will understand in the next slide. And as we have discussed, this is a symbol of a symbolic representation to draw to show the diode. That this bar line shows a cathode, and opposite to this will be an anode. So this is plus symbol and this is minus symbol. If you take the physically, like in the first slide, I've shown few of the pictures of the diode. So whichever side there is a strip mark, so that is cathode, and opposite to this particular strip mark is called as an anode. Like in the case of resistance, to know the value of resistance physically without using a multimeter, what we follow, we first see that which side it is having a gold mark or silver mark. So whichever side we have a gold or silver mark, that is nothing but a tolerance, 5 or 10%. Opposite to that, we start the counting and we take the color coding, and according to the color coding, we measure the value of resistance. So similar way to identify which is cathode and anode, in the case of diode, whichever side we have a strip, that is a cathode, and the other side is an anode. Now, let us see the construction. Before that, we can go for this diffusion. See what happens. This is p-type. This side is p-type. This is an N-type, this is a junction, this is a cathode, and this is an anode. So how the diffusion takes place? Movement of electrons from one region of higher concentration to a lower concentration happens. And at the junction, the electrons from the N-type and holes from P-type attract each other, combine and cancel their net charges. So what basically is happening is, we can see that what basically is happening, normally this PN diode is so prepared artificially such that one part of it may generate electrons and the other part is to collect them. That's what the simple, we say anode and cathode. Cathode will generate an electrons and anode will collect it. PN junction conducts electric current much more readily in one direction than the other direction. Now what is happening, if you see this figure, what is happening, how the diffusion takes place? The N-type material has a high concentration of free electrons and P-type material has a high concentration of holes. Therefore, what is happening? Therefore, at the junction, the free electrons from N side diffuse over to P side and holes from P side diffuse over to N side. Because of the opposite like charges, they try to recombine each other. They diffuse from one to another because of the opposite charges. Hence, a positive charge is built up on the N side of the junction and a net negative charge is established on the P side of the junction. The electrons and holes which are at the junction may recombine and the region D becomes free from the mobile charge carriers. Now here what is happening at the junction, one of the hole and one of the electron will recombine each other and become neutral. So at the junction, I can see that a potential barrier is set up. This is how it looks. See, due to the cancellation of electrons and holes at the junction will have no more carriers. So it is called depleted region or depleted layer, we can say that. Depletion in the sense free. Free from what? Free from any mobile charge carriers. So this region depleted of any mobile charge carriers is known as depleted layer. Now what happened on the next side? The positive charge on the N side repels holes to cross from P to N side, and the negative charge on P side repels free electrons to enter from N side to P side. Because of opposite electric charges on either side of the depletion layer, here an electric, if you see here, an electric field is formed. Thus a barrier is set up against the further movement of charge carriers, and this barrier is called as a potential barrier. Because here we can see that it is depleted from any mobile charge carriers, we can have a net electric field or a potential barrier is set up, and this potential barrier will not allow the further diffusion of P holes from P side or electrons from N side. So there won't be any further movement of charge carriers or any further diffusion from one side to another side, any mobile charge carriers. This is just a VI characteristics. Later we will very clearly understand how the PN diode behave when we provide a source to that. So potential barrier for silicon is different values, 0.7 electron volt, and for germanium it is 0.3. We get a forward bias into the first quadrant and reverse bias into the third quadrant. We will have the same graph again. We'll repeat it. So if we summarize everything, this is how the connection is given. We have given a source. This is a source and this is a diode. The positive is connected to this positive P type, and then there is a load resistance. So we will see again the same thing into the next slide. If you summarize everything, what is that? Depletion region and the junction voltage. How it is happening? At the PN junction, electrons from the N-type semiconductor will attract to the holes in the P-type semiconductor. As a result, the holes and electrons at the PN junction disappear, forming a layer called depletion layer. At the same time, the P-type semiconductor becomes more negative whereas the n-type semiconductor becomes more positive. This will result a potential difference across the p-n junction. This potential difference is called the junction voltage or barrier voltage or potential voltage. We have discussed this. The junction voltage will prevent the charge carriers from flowing across the depletion layer. As we discussed, there won't be any further movement of charge carriers from one to another region because of the junction barrier it developed on the depletion layer. Now we can have the connection of the particular p-n diode in a two bias way. We have seen the construction of p-n diode, but how it behaves when I give a source in a different manner. So that can be called as in forward bias and reverse bias. If we take first example as in forward bias, to connect a p-n diode into a forward bias, the p-type material should be connected to the positive polarity of the battery and n-type material should be connected to the negative polarity of the battery. Now in this picture you can see this is a p-type and this is an n-type. P is nothing but an anode, N is nothing but a cathode. Here I can see that the P is connected to the positive polarity and N is connected to the negative polarity. So the same thing we have discussed, P is more positive than the N-type. The condition that allows current to flow the p-n junction, and the p-n junction narrows. The junction will become very narrow in the case of forward bias. We'll see in the next slide. So how the construction of p-n diode in a forward bias should be made as anode must be positive with respect to the cathode, and the potential difference should be greater than the threshold voltage. What is the threshold voltage? Normally we abbreviate it as in VTH. The threshold voltage, which is nothing but required voltage across the junction of the diode before forward current can flow significantly. I mean, the potential difference, the source what we have given to the particular diode should be greater than the threshold voltage. Unless we cross that particular threshold voltage, there won't be any current flowing in a forward bias. So these are the conditions of the forward bias. So how we will make the definition of the forward bias, how the definition of the forward bias goes, again I'm going back. This is what. So because now what is happening, because the p-type material is connected to the positive polarity, both are light charges. So all the holes in the p-type will be moving towards the junction. Similarly, all the electrons which are the majority charge carriers in the n-type will be moving towards the junction. So when all the holes as well as all the electrons which are the majority charge carriers in the respect to p and n-type region will be moving towards the junction, it makes that the depletion layer will be slowly, it makes decreasing, and at certain point there won't be any depletion layer left out between the p and n region when it is connected to a forward bias. So once we give a potential difference more than that particular threshold voltage, we can see that the current is flowing. So in the case of forward bias, we can say that the current is having a higher value and which flows in the circuit. So how the definition goes for the forward bias? When a potential difference across the diode is connected in such a manner which cancels the potential barrier and allows the current to flow in the circuit is called forward bias. To construct the diode into the forward bias, p-type should be connected to positive polarity and n-type should be connected to negative polarity. This is the basic things of the forward bias. Now if you have a reverse bias connection, and the same diode, if you take an example and we have connected in the reverse bias. Reverse bias in the sense, the construction is happening in such a way, like p-type is connected to negative polarity and n-type here is connected to a positive polarity. Now what is happening? P-type is more negative than the n-type. A condition that prevents current to flow through the p-n junction. The p-n junction widens. It means what is widens? The depletion layer increases. How the depletion layer increases? Because all the holes which are the majority charge carriers in the p-type will be attracted to the negative polarity of the battery, because these are opposite charges. And here in the case of n-type, all the majority charge carriers as an electrons will be attracting toward the positive polarity of the battery. So here we can see that the holes as well as the electrons are moving away from the junction. Away from the junction, it means it is making the depletion layer into a more, it is increasing the depletion layer, it is increasing the width of the depletion layer. These are the conditions. Cathode must be positive with respect to anode. The potential difference should be greater than the diode's breakdown voltage. Now, what is breakdown voltage? Maximum voltage the junction diode can handle when it is reverse biased, also called peak reverse voltage and peak inverse voltage. We will see this in the graph when we plot a VI characteristics of this particular junction diode. If you compare between the germanium and silicon, widely used as in semiconductor materials, silicon has relatively high breakdown than the germanium. Silicon, obvious, silicon we get it from silicon dioxide, from the sand at the seashore, and germanium is nothing but it's kind of an ash coal. With that we get this particular material. This we have seen how the operations in the forward bias and the reverse bias are done, how the barrier is set up and the blockage and all those things. Once again, we repeat the same thing. The polarity of applied voltage which causes charge to flow through the diode is called forward bias. Charge to flow, it means it is allowing the current to flow in the circuit, is called a forward bias. The polarity of applied voltage which can't produce any current in the reverse bias is called, this is called reverse bias mode or reverse bias condition. So here, once again, I will repeat the forward and reverse bias. In the case of forward bias, we measure a current through an milliammeter, 10 to the power of -3 amps, whereas we also measure a current in the case of reverse bias. How it is possible? Because we were talking about, as both the holes and the electrons are moving away from the junction, it widens the depletion layer. But still, we measure a current with the value of microamps, 10 to the power of -6 amps. How is that? Means, as we know that the p-type material are having a majority as in holes, but what are the minority? Minority are electrons. In the same way, in the case of n-type, the majority charge carriers are electrons, but the minority charge carriers are holes. So these minority charge carriers will make a small amount of current in the circuit, which is measured by the microamp. Now we'll see the IV characteristics, VI characteristics of a PN junction. See, this is how it comes like. So again, we have just to summarize everything. This is a PN diode. This is a symbol of the diode, and this is the physical appearance of the diode. This is a line strip. Opposite to strip is an anode. This is the cathode, and this is a VI characteristics. Now see the. When the voltage is 0, we have taken voltage on x-axis and current into the y-axis. Here, in the case of forward bias, this I current should be in the milliamps. And obviously, this is V plus V, so this is third quadrant, second quadrant, so this is minus V. Opposite to that, this is I, and opposite to that, this is a minus I. And this we have to take in the form of microamps. So I in microamps, here the I in milliamps, V in voltage, this is also in volts. So see, here you can see that when V is 0, the I is also 0. The V is 0 in the first quadrant. Please look into the first quadrant. I could not use the annotation over there, so please bear this. So here you can see when V is 0, the I is 0. After this knee voltage, this is called knee voltage. I mean, like, you know, when the potential difference is crossing the threshold voltage, then the current shoots up. So this is where we can say that this is a knee voltage, and after this knee voltage, the current rises rapidly in this manner. So this is called forward voltage drop, which is there in the quadrant first. And this point where the current rises rapidly is called as a knee voltage. In the case of reverse bias, we can see that it is 0 and 0, and here we will be getting a reverse breakdown voltage. This is called a leakage current. There will be some leakage, and then here we can see that the current is rising. Actually, they have given this, we can say, like a zener. In the case of PN, it is gradually as the voltage is increased, the current is also increasing in a third quadrant. So minus B and minus I. So this is called as a reverse breakdown voltage. Got it? Now we will see exactly every part of that, like forward voltage drop, knee voltage, leakage current, reverse breakdown voltage, and all definition we have it. So what is forward region? It is the operation region at which the potential applied to anode is more positive than that applied to the cathode. Reverse region, it is the operation region at which anode potential is more negative than the cathode potential because it is in the reverse. We have a saturation part of reverse region where the diode impedance is very high and causes a very small drift current. That is called as saturation. Diode impedance. What is impedance? Impedance is nothing but resistance produced. If we say that a resistance produced due to a particular capacitor or a particular resistance, or we can say that the resistance produced because of the inductance. So it is called inductive reactance. If it is produced because of the capacitor, it is called capacitive reactance. So if we have physically a resistance, a capacitance, and an inductance, and if you are asking what is the total resistance in the circuit, physically there is a R value resistance, then the resistance produced due to the capacitance after it attains to a maximum charge, then again a reactance which blocks the flow of the current, which also blocks. So resistance produced due to the inductance, resistance produced due to the capacitance, and there is a resistance, internal resistance. A joint effect of all this is called an impedance. A joint effect of resistance and a reactance is called impedance. What is breakdown region? The part of the reverse region where the diode impedance is very low and the current passing through the diode is very high. Obvious, if the resistance is low, the current will be high. Impedance is nothing but a resistance, which is nothing but a joint effect of resistance and reactance. Threshold voltage. It is also called the knee region. It can be determined on the IV curve by the point at which diode starts to conduct current easily. It is also called the diode barrier potential and is very near in amplitude to the diode built-in voltage. We have saturation current. It is a very small current due to drift current in the diode in the reverse bias region. This current is very low in the nanoamperes range due to the high impedance of the depletion layer, because there is a high value. The impedance is very high in the region of depletion. So current is very low, such a low that we have to measure with a nanoampere, like 10 to the power of -9. Breakdown voltage. It is the maximum allowable voltage in the reverse bias region at which diode resistance change abruptly from very high impedance to a very low impedance. If the reverse voltage applied on the diode exceeds this limit, a very high current in the reverse direction passes through the diode, causing in burning.